Hello everyone, my name is Rani. I am studying at Institute of Aeronautical Engineering, BTech second year CSE. So today I am going to give presentation on low content semaphores and ready queue. Let's see. Contents are introduction, ready list and semaphore list, starting, stopping and scheduling process. These are the operations. Waiting signal and wait and signal process also operations, and ready list ring conclusion. Coming to introduction, modern operating systems implement semaphores for synchronizing multiple concurrent processes. Here, processes are nothing but a specific task. You know, so modern operating systems are implementing semaphores for synchronizing multiple concurrent processes one after another to synchronize the process in the sequence. So they are using semaphores. Unless the primitive operations for starting, stopping, and scheduling process and for manipulating semaphores are well supported by the hardware, context switching and interprocess signaling can be major of it. Even though we solve this operation starting, stopping, scheduling processes, but here context switching and interprocess signaling is a major over it. Context switching is nothing but switching between the two processes based on their priority, and interprocess signal is nothing but communication between the two processes can be a major overhead. To avoid these overheads, many operating systems use fast but unreliable ad hoc methods for synchronizing process. So many operating system use different types methods, but they are not unreliable for synchronizing process. The number of processors CPU that can be kept busy can be limited by contention at the ready list or at semaphores. So the number of processors CPUs that can be kept busy can be limited by contention at the ready list or at semaphores. By using ready list, we are going to solve the problem of this process overhead. Ready list and semaphore list. The ready list is a queue containing indices of all processes enabled to run on a processor. It is a queue for which the processor in the queue to take the CPU time, to take the resources of CPU and get executed. It emanates from a descriptor containing a head, tail, linked list specifier, and a log bit. The queue itself is a chain of processes found by tracing through successive link fields starting from the head process and terminating at the tail process. So it has head and the tail, and it has link between the process head to tail. The semaphore list is an array of semaphore descriptors. Each containing a count field registering the excess of sent over received signals. A head-tail linked list specifies defining a queue of processes waiting for signals. Here, the process of waiting for signals, and a log bit to prevent simultaneous access by two or more processors. So here also the head tail will be there, and here also log bit will be there for to not access the CPU by two or more processors. Starting, stopping, scheduling process. So these are the operations. So let's see. We suppose that there are three uninterruptible operations for manipulating the process list and the ready list. These operations refer to a processor register self that contains the process index of the process concurrently funding on that processor. If funding process is not on the ready list, the instructions are save as W used to stop process from running. So save as W is nothing but used to stop a process from running. The processor registers are copied into PL state word. Load as W used to start a process running, loading. Load is in the sense starting the process. Used to start a process running, removes the head process from RL ready list, and sets self to this value, loads the processor registers from PL stateward and proceeds. Ready used to schedule a process. Inserts a process index I at the tail of the R. Wait and signal process. The wait operation is used to receive a signal from a semaphore. The calling process will be delayed if the count is 0 or less at the time of the attempted reception. The signal operation is used to transmit a signal through a semaphore. The head waiting process is released if the count is less than 0 at the time of attempted transmission. Both operations are must be indivisible in the sense that while a wait or signal is in progress on a given semaphore, no other wait or signal on the same semaphore may be initiated. This implies that both operations must be uninterrupted. This is that wait and signal process are uninterruptible. Even though these three operations, starting, stopping, scheduling, are also uninterruptible operations. So here we see an example of semaphores. Semaphore, as we see, it's a array of semaphore descriptor. So here a thread is nothing but doing some specific task. As we said, process is doing some specific task, but lightweight process are known as thread. So in the semaphore contains 0, 1, 2, 3, 4. So these are like a thread, and they have a wait release. Wait release means resources. Here CPU is allocating the resources, right? So wait here thread is waiting for the resources which it doesn't have, and release the resource which it is used and completed the execution, and it should give to the another thread for completion of another thread execution. So if it is a shared resources, this is how the operations has been performed. Process. So let's see the process. First, the instruction save SW is uninterruptible. Once begun on a given processor, because it is a microprogram that does not inspect the interrupt indicators. So it is a microprogram that does not inspect the interrupt indicators. It doesn't see for the interrupt indicators. It cannot inspect it. The programs load SW and ready are uninterruptible. Once begin because they are enclosed in lock unlock pairs. Second, ready list manipulations are mutually excluded because the ready list is locked by load SW and ready. The only two programs that operate on it. So load SW in the sense loading, in the sense starting the process. Ready in the sense the process is in the queue, in the ready queue. While these locks are set, interrupts are disabled by the lock instruction. So interrupts are disabled by using the lock instruction. Third, the critical section of the wait and signal programs are enclosed by a lock unlock pair. So as we say log bit. Now by using that, it is uninterruptible. This ensures their mutual exclusion for any given semaphore and prevents interruption of the processor inside the critical section. So by using lock and unlock a pair, process cannot interrupt. Interruption of the processor inside the critical section prevents it just prevents the interruption between any operation, that may be the wait, signal, load, ready, save. It is. And next, fourth, each process index is either in some one self register on the ready list or on someone semaphore list. The moving of a process index between pairs of these places cannot be interfered with for the reason summarized in table 1. Deadlock is not possible because holding of ready list locks is strictly nested inside the holding of semaphore locks, because its interrupts are disabled when it while it is in a Locker region. A processor cannot be diverted into another program containing an attempted lock on another semaphore or on the ready list. Means while the operations are performing, wait, signal, start, no operation can be interrupted, and cannot stop the operation, right? Cannot stop the operation. So the CPU is giving to the respective thread or respective process until and unless it completes, it will not go to the another process. And here a ready list contains locks bit, uh, which enables the CPU, which gives the CPU to does not interrupt it. Ready list ring. Ready list lock contention can still be a problem if there is a lot of process switching. As I said, context switching and process switching are the same. The contention can be eliminated if each processor has a private window into the ready list, such that each window contains at most one process index, and process index move among the windows. Means each processor has a private window into the ready list. Each processor such that each window contains at most one process index, and process index move among the windows. So windows contains one process and which move among the windows, One possible implementation of this principle is a circulating ring of slots packets, each capable of holding the index of a ready process and its priority number. Each processor has its own port into the ring. Two of the previous operations are defined. Load SW. Wait until a used slot comes. Self priority registers and mark the slot as unused. Load register from PL self stateward and proceed. Wait until slot comes. As I said, it's forming the ring. It's forming the ring of processors, and each window has one process, and um, based on the slot, based on the resources which has been used, and waiting and releasing, right? Waiting and releasing and priority according to, if a thread having high priority, then it will be the context switching, right? It should be executed first, then after the another thread should execute it. So in such a way. Conclusion: we have demonstrated that a modest amount of hardware support can significantly reduce the space and time requirements of primitive operations for process, context switching, and semaphore management. Start, stop, schedule, wait, and signal operations are efficient enough to permit process management without shortcuts and to permit a greater number of processes to be used. So these are the five operations which normally a CPU performs for the processes which are there in the processes for doing a specific task. For doing a specific task, they assign the process will be there in a ready queue. They assign to the CPU at the given time, and after the completion of the CPU, the resources will be released from that process, and that resources will be allocated to the next process, and the process will take a CPU time, take and utilizes the resources, and again releases the resources, and again the next process will utilize the resources, take the CPU. In such a way the process will be continuous. Thank you.